today's algorithm, there's no big kind of new idea here. Like we did Simon's algorithm, there's a new idea. The Grover's algorithm, there's a slightly different new idea. Here today, really, it's just this well kind of known notion since Grover's algorithm that, hey, anytime you need to do a search, Grover's algorithm over a black box, Grover's algorithm will provide you with this generic quadratic speedup. And today's application of Grover's algorithm to MaxCut is exactly an example of just that. We're not really doing a new algorithm per se. We're really just applying Grover's algorithm to a known problem with the expectation that, hey, because of the quadratic speedup that Grover gives, we'll carry over that speedup in the algorithmic runtime of MaxCut as well. And yeah, so we'll see as that goes along. But first, let's finish off the part of Grover's algorithm that we missed out on yesterday. Quick recap, this was the structure of Grover's algorithm. Apply Hadamard to our initial all zero states. Apply this specific transformation for Grover's algorithm, k number of times, and then measure. We identify two different kind of specific entries here, Z0, ZF. Z0 we'll have more to talk about today. ZF is the oracle for the function that we're interested in. All right, and so we are going to do a little bit of playing around with the G. Our perspective of Grover's algorithm, our interpretation of Grover's algorithm led to a nice analysis in terms of rotation that G essentially ends up applying on the state that we have. But another interpretation, which if I recall correctly, was the original kind of motivation of how Grover ended up with Grover's algorithm was based on kind of this diffusion operator where you decompose G into U times Z sub F, where Z sub F is your oracle and U is kind of the remainder part of G. And this thing is known in, I guess, crystal lattice study in physics already. I'm not sure, not an expert there, known as the diffusion operator. We'll definitely look at the application of diffusion operator for our purpose. We've already worked out that this diffusion operator over here will look something like this. And if you just think about it a little bit, you know, you've got this H, which is the uniform superposition string. You've got it multiplied with the column vector and the row vector. That will end up resulting in kind of this all one matrix with the factor of 2 to the 2 divided by n factor outside. So we want to get a slightly better understanding of what's the result of applying this matrix transformation to an arbitrary quantum state. What was f of x defined as? So in our case for Grover's algorithm, we understand f of x as an arbitrary Boolean function. There's no additional promise. So if you've got n bits, then you're saying f of x is a Boolean function that maps a binary length n string to a single output bit 0 or 1. And we're interested in finding one instance of input string x for which the f does evaluate to 1. Kind of like sometimes you refer to as a marked item, looking for a needle in a haystack, the specific string x that you were searching for which the function evaluates to 1, all kind of equivalent ways of thinking about it. Okay, so let's kind of just try to work it out. I've got this U. I will apply to an arbitrary quantum state. Well, it will be in a superposition. Some amplitudes alpha sub x and ranging over the basis states x. Right? Through linearity, you can bring in the U, and so you've got U directly applied to x. Right? Now, U directly applied to x, let's kind of plug in this definition of U in here. So you've got sigma x 2 over n, the all one matrix minus identity applied to x. Obviously, identity applied to x will be the same thing. What you want to kind of think about a little bit is what will be the effect of applying this transformation to x. And this is an exercise in your notebook as well. If you think about it, it's obviously straightforward. You've got kind of you'll end up with the summation of these these capital N entries, all of them with this 2 over n in front of them. You take out the factor of 2 and alpha x, so it's kind of like you averaging out over all the superpositions. So you get sigma x let's choose color. And then you write 2 mu minus alpha x, where what is mu? Well, mu is exactly the mean. It's 1 over n times sigma x alpha sub x. So it's nice to know that what will happen to the amplitude in front of a state x when you apply this diffusion operator to it. If the amplitude initially was alpha sub x, it will become this. Let's visualize this to get a nice interpretation, which is different from the rotation interpretation that we had yesterday. Right, so initially we create the state H, which, if you recall, was this uniform superposition state. Right, yeah, f of x is equal to 1 if it's a good state. That's exactly one way we identified it in the analysis yesterday. So after getting a uniform superposition, we apply this inversion operator. And the way to think about it is, once you apply z sub f first before the inversion around the mean, recall applying z sub f had what effect? Because before applying u, we apply z sub f, right? What was z sub f? Z sub f, here we have, was just minus. It's the oracle call, which puts a -1 sign in front of the cases where f of x evaluates to 1. So applying z sub f to state x results in this state. Let's assume x star was exactly that one marked state, exactly what's being discussed in the chart as well. You know, this was that one good state for which f of x evaluates to 1. Well, when you apply z sub f to it, to the state h, it will leave all the other amplitudes unchanged, but it will flip the sign in front of this marked state. So it will go from plus 1 over square root of n of x to minus 1 over square root of n of x, right? And then we apply the inversion around the mean operator. Obviously, previously the mean was exactly 1 over square root of n. Now, because it's a large database, one entry has just flipped its sign, so the average will be slightly lower than before. But let's assume, for the moment, we assume that the average is 1 over square root of n. It's a small enough error. What will happen? Well, let's just do the analysis of that expression that we had calculated in the previous slide. We know that in front of the marked item, the new amplitude will be 2 mu minus alpha sub x. Well, what's the average? Let's assume it's just 1 over square root of n, which it is approximately. The amplitude in front is not 1 over square root of n, but minus 1 over square root of n. So you get minus of minus 1 over square root of n over here. And see that the constructive interference ends up making this 3 over square root of n. So that an amplitude that was previously uniform, after applying this inversion around the mean, has been amplified for the marked item that we're interested in finding, that it has gone from 1 over square root of n to 3 over square root of n. And I welcome you to do the exercise that if I now carry on with this procedure, where I take this state and apply z sub f, well, what will happen? This will get flipped again. It will become minus 3 over square root of n. And then I apply the inversion around the mean operator. So you'll have 2 over 1 over square root of n minus 3 over square root of n, ending up with a 5 divided by square root of n amplitude. And so you get this amplitude amplification happening. Obviously, it won't keep happening always. At some point, once your state starts rotating away from being a good state, then this averaging out will actually result in this spike moving back towards the mean. And so you've got this kind of cyclic behavior, which you can work out in detail as an exercise. We'll stop there for that inversion around the mean operator. How do we implement this inversion around the mean? We have this operator representation for it, which we recall yesterday can be written as this as well. because that's in fact how we got this. We had actually gone from here to here. Now, how will we actually implement it as a step towards figuring out how will we actually implement the oracle as well for Grover's algorithm for max cut? Well, this is the trivial part, for sure. You've got Hadamard's over here. This over here is exactly the definition of Z naught. The green line, I see, let's go back. So this green line is referring to the fact that your average now is actually, we are making a slight assumption in calculating this 3 over square root of n and 5 over square root of n, because the new mean is actually slightly lower than just 1 over square root of n, right? Because previously all the amplitudes were uniformly 1 over square root of n, so the mean is also 1 over square root of n. But now one of the amplitudes has gotten flipped to minus 1 over square root of n, so the mean would actually be slightly lower. So the green line is referring to that lower average mean point. It's around the line according to around which our amplitude is getting flipped, right? Inversion around the mean. Okay. So what's the intuition about this circuit for this diffusion operator? We know what Z naught is supposed to do. Z naught has this effect that if the input state is any state other than the all zero state, it does nothing to its identity. But if the input state is the all zero state, then it introduces a minus sign in front of it. And so this is a good, understanding this is a good step to build towards our implementation of Z sub f for the particular application of max cut as well. And so you try to kind of just step back and think about what do we need to do? If all the qubits are 0, then introduce a minus sign in front of the state. Well, we have control operations, which is being applied over here, but control application operators work when conditioning on when the state is all 1. But here our requirement is it's all 0. Not a problem. That's exactly why we have got these sigma x operators over here. So if all these states were 0, applying x to all of them will become 1. So if all of them are 1, hence we are controlling on all of them. This is 1, this is 1, and this is 1. And now you might be like, well, why isn't there control over here? We want this to be 1 as well. Well, in the case if this was a 0 and we applied a Z transformation to it, nothing will change. It will remain 0. But if the state was a 1 because of the transformation over here by x, then Z applied to 1 will become minus 1, hence introducing the minus sign that we're looking for. So this entire part of the circuit is implementing Z naught for us, and then Hadamard layered on the front and the end allow us to conclude that this entire transformation is given by this circuit. All right. Any questions about the circuit representation of the diffusion operator? This way of thinking about how to apply this particular transformation set of gates to implement this transformation is useful moving forward now when we'll apply Grover to max cut. And that's exactly what we move towards now. As I mentioned, we're not really doing a new algorithm. We are really applying an algorithm to an existing known problem. And so let's do kind of a tangent to what's the mathematical background we need to know and the notation we need to know to define the max cut problem. We are talking about graphs, undirected graphs in computer science perspective, i.e. a graph is a set of vertices and a set of edges, or a set of nodes and set of edges. Vertices, let's say V1 to Vn, or nodes V1 to Vn, and the edges we are considering are undirected, so it doesn't matter whether you're going from V1 to V3 or V3 to V1, it's the same edge, order doesn't matter, and these two together define a graph for us. Here are some particular examples that, and I'm sure most of you are already familiar with this. If not, now you've seen what a graph is. There are definitely many other variations that you can define. Directed graphs, these are simple graphs. You can have other definitions as well. You can also have capacities on these graphs as well, on these edges as well. We won't worry about them. So we got the simple definition of an undirected graph. And on this, I define this notion of a cut. We want to talk about the max cut, so we should be clear about what a cut is. A cut is just a partition of the set of vertices of the graph into two non-empty sets, such that you're really still spanning the entire set of vertices, right? So if you say one set is S, some subset of V, then the remaining set of vertices will be R, V minus S, right? So example, in this particular graph, you had vertices 1, 2, 3. One trivial cut would be to say, all right, I have one partition in which I only have vertex 1, and another, the second partition then will obviously contain vertices 2 and 3. Over here, I've got 4 vertices. I could choose to have vertex 0 and 1 in one partition, and then the remaining 2 vertices, 2 and 3, will be in the other partition, right? Now, what's the size of a cut? The size of a cut are the number of edges that are going between S and R. What do I mean by that? So here, I had S, a single vertex. There's only one edge coming out of it. So you can think of it as like going across this boundary of this partition that's going from S to R. So really, the size of the cut in this case is just 1. A bit more interesting case over here, you think about kind of this dotted line identifying the partition. So thinking this edge is going across from 0 to 2. 0 is in S, 2 is in R. The edge connecting 2 and 3 doesn't count because it's within the same partition. 1 and 3, the edge containing the edge between 1 and 3 counts because it's going across the partition. Similarly, 0 to 3 counts as well. So this cut has size 3, right? So these 3 edges constitute that cut. This edge and this edge does not contribute. However, since we're interested in max cut, intuitively enough, max cut would be given a graph, finding a partition such that we have maximized the number of edges in the cut. So considering that same graph, we had this partitioning, which allowed us to identify a cut of size 3. Within that same graph, you could now identify a different partitioning where you say, all right, I do this partitioning, where now rather than referring to these partitions as S and R, we can also think of them as just being colored, right? That's going to be equivalent. So one is a set of vertices that colored blue, the other is the set of vertices that's colored red. And now let's see what's happening. Going from 0 to 2, I've got this edge, so that would count. 2 to 3, that will count. 3 to 1, that will count. 0 to 1, that will count. The only one that doesn't count is the one going from 0 to 3. So here I've got a cut of size 4. So over here I had a cut of this size 3. I played around with the partitioning and I am able to find a larger cut. The problem of max cut is to really find, given a graph, the largest possible cut for a graph. For another example, let's see this graph. Right, so now I have 5 vertices. Any takers on Discord about what's the maximum cut for this graph? What's the size of the maximum cut? Oh, nice. 3, 5, 6, 4. 3 over 2. I'm not sure you got 3 over 2. Okay, let's do one example. Here's one cut. I make 4 and 5 into one partition, 1, 2, and 3 and the other partition. And so I'm able to get this edge, and this edge is contributing to the cut, leads to a partition cut of size 3. However, I can also identify a different partitioning. If I have 2 and 5 in one partition, and 1, 4, and 3 in a separate partition, so I will then note 1 and the edge between 1 and 4 won't count. 1 and 2 will count. 2 and 3 will count. 3 and 5 will count. 5 and 4, and 2 and 4. So here the size of cut then becomes 5. Right? Again, you can identify the partitions as the sets because we want to connect it to our application of Grover's algorithm. It's also nice to be able to think about, hey, the set of edges, the set of vertices get mapped to 0. So think about it in terms of coloring. So if you are in, let's say, this red color case, the red color is kind of getting mapped to output 0, and the blue color case is getting mapped to output 1. Nothing particular about this choice. You can flip it, but just in order to move towards the notation that we need to have for the purpose of applying Grover's algorithm to this problem. And that's going to be the major task for us today, to figure out the right representation for this problem to be able to apply Grover's algorithm to it. And then we'll be able to see how to construct the oracle for this problem as well. Right. Okay. Not necessarily, no. So you need to span, so recall the definition. You have two sets, S and R. They're disjoint sets, and you should get all the set of vertices within that partition, right? Okay. All right, so a couple of, again, side notes. The way we have identified the max-cut problem right now, it's kind of, it's an optimization problem, right? So most of the times, computer scientists work with either decision problems or optimization problems. Decision problems are of the form where the answer is just a yes or no. Optimization problem, the way we have formulated max-cut so far, find the largest k such that a certain property holds true. That's optimization. There is a nice mapping between the two in terms of binary search. So if you've got a problem that's stated in its optimization form, you can always convert it into an equivalent decision problem, as long as you're able to take on a logarithmic overhead because of binary search. And we'll talk more about that later, but the idea essentially becomes, as stated over here, that rather than just asking, hey, find me the maximum cut of a given graph, I restate the problem in terms of decision problem, find me a cut of size at least k. And then I can do a binary search over the size of k to be able to zone in to the maximum size for k. And so that binary search that I will have to do to figure out the maximum k is the overhead that I have in the decision problem in order to solve the optimization variant of it. The decision problem isn't giving you the optimality right away, right? Decision problem is just you asking, hey, do I have a cutoff size, some constant k? The answer will come out yes or no. And then you can kind of do a binary search on this, the size of k, to identify the optimal or the maximum k. Binary search, I think I've got a nice slide later on that will hopefully explain it, but think about it. Right, so what's the intro to CS binary search example? You've got a phone directory, a physical phone directory, if you could imagine that existing, right? So the idea is so it's a nice contrast to Grover's algorithm as well. Grover's algorithm, the idea was that the data is unstructured, there's no order necessarily. Assume your data is ordered, for example, names in a telephone directory, and you're looking for a certain name. And one way to do the search is you basically kind of divide your space right in the middle, right? So if you are looking for numbers, letters from A to Z, you you identify the letter right in the middle. Does my thing exist in the left of it, or does it exist to the right of it? And then you kind of recursively keep doing this search to the left or the right of whichever case, whichever set will contain your answer, such that within a logarithmic number of iterations of this process, you essentially get the answer whether or not your element is in this set or not. We will actually do an example, hopefully, of this by the end as well, so hopefully this will become more clear. I'd forgotten to include our discussion on binary search. To choose k, exactly, to choose k in this case would be an iterative process exactly via binary search. And we'll see this by the end as well. Now, we're interested in this max cut problem because we know it is NP complete. So many smart people have tried, but they haven't been able to figure out a nice, efficient algorithm for this problem. We expect that there won't be, but we don't have a proof. And the idea here will be, well, I will be able to apply Grover's algorithm to get this quadratic speed up. So the classical algorithm for most NP-complete problems is going to be O of 2 to the n. With the quadratic speed up from Grover, I'll get this square root of 2 to the n runtime. And really the idea, hopefully within the next slide, will become clear in terms of how Grover is being applied to it. No, this is the max cut problem. There is a similar sounding but different problem called the min cut max flow problem. And that has been well studied, and both of these problems have really practical applications. Min cut, though, is nicely solvable by an efficient algorithm using Ford-Fulkerson and many other variations of that algorithm. That's not really the topic of interest for this talk, but that algorithm also is very nice. It's a nice, efficient algorithm for solving the min cut max flow problem. All right, so let's get to the main problem that people had been asking about since yesterday. Reza, no, so in this case, we know it's NP complete. So this problem is NP, and you can check that, right? So it's easy to verify whether a given solution is a valid solution for the max cut problem. So it's NP complete because it is an NP. So the issue for us is if you want to apply the Grover's algorithm to this, we want to be able to construct the oracle. How will we construct it? Now, one connection you can also have is in terms of where this exponential complexity is coming from, is think in terms of the colorings of these vertices, right? So imagine the colorings. If you think about the graph becoming too colorable, then identifying the two coloring for the graph allows you to identify the two partitions as well, right? How many possible two colorings are there of a given graph? There are 2 to the n possibilities, and so that's the 2 to the n different possibilities that you have to search over. The reason why Grover will give us this quadratic speedup is because we'll take this 2 to the n size search space and put all of these entries in superposition. It's not still clear, right? Which entries are we putting in superposition? I'll define that soon. And then apply Grover's algorithm to that superposition to get that speed up. Right, so first matter about our representation. We need to represent vertices, we need to represent edges, and then based on that vertex and edge representation, figure out how to calculate the size of the cut. Given n vertices, we'll first take n vertices, n qubits to represent those n vertices, 1 qubit for one vertex. We'll have this convention that the qubit will, for a corresponding vertex, should be in the state 0 if it's colored red. You might ask, well, how do I know it's colored red? But we are just setting the convention. You'll soon see what do we mean, how do we use this. If the state of a vertex is 0, then that means it's colored red. If the same state for that vertex is in state 1, then we think of it as being colored blue, essentially identifying the 2 different partitions to which it might belong. So for example, if you've got this size 4 graph with these 4 vertices, then you've got the vertex 0 and vertex 3 colored red. Well, that should be the 0 state. Vertex 1 and vertex 2 being colored blue, so that should be the 1 state. So that gives you this representation for the set of 4 vertices. So the 4 vertices of this graph will be represented by this state, right? So that's a vertex representation. Now we have to figure out how are these vertices being used to represent, or how do we use additional qubits to represent edge information about a given graph. Before we do that, let's restrict our attention to a special case of the set of graphs that we'll consider, i.e. essentially bipartite graphs. And here the idea is very similar to how we are identifying cuts, in the sense that graph is bipartite if the set of vertices could be partitioned or equivalently colored, as we've been talking about it, into 2 disjoint sets. That's exactly the way we've been defining a cut. What's the additional requirement? Such that these 2 different partitions that we identify, S and R, there is no edge connecting the vertices in S, and there is no edge connecting the vertices within R. So sure, there might be edges going from S to R, as for example, in this graph, I identify this as my S and this as my R, right? So there's vertex going from here to here, here to here, here to here, but there's no edge connecting these 2 or these 2. On the other hand, This graph is not bipartite because if I try to do this, yes, there's no edge between these two, but then between this, there is an edge between here. So it doesn't satisfy the requirement of being a bipartite graph. This can be used to solve the traveling salesman problem. Since all NP-complete problems are equivalent, in some sense, yes. But as you will see, hopefully by the end of this discussion, there is no new algorithmic idea in our discussion here. So the major problem for us in this construction is actually to figure out the correct way to represent information about the max cut problem in our quantum circuit. Right? And so it won't really be worthwhile to take this representation and then figure out how to map it, how to map the traveling salesman problem to this representation. It might be more useful to directly attack the traveling salesman problem, given that the speed up that we are obtaining over here is a generic speed up because of Grover, not because of any additional interesting thing that we are doing. All right, so bipartite graphs, obviously by definition, would then also admit two colorings. Just take the two partitions that we have identified and identify them to be, partition 1 has color blue, partition 2 has color red. And if you're okay with that, you can, so just like you would have selected 2 and 4, you could have for sure selected 1 and 4 as well, but then 2 and 3 have an edge in between them, right? So yeah, you get one partition satisfying the requirement, but the other partition doesn't satisfy that requirement. And so for the case of bipartite graphs, you now, the reason why we're doing this is we make this simple kind of observation. When a graph is bipartite, you identify the two partitions, and then the edges are essentially, all of the edges are going to be going across the two partitions, right? And so all of those edges contribute to the cut. So the size of the cut will be essentially the number of edges in the bipartite graph. And so the problem essentially becomes, is the graph bipartite or not? Right? Okay. So towards that purpose, our next little gadget that we'll use is edge checking, where we are essentially implementing the logic. We've already figured out, if a vertex is colored blue and a vertex is colored red, and then if an edge is between them, we want to identify this property that the edge connecting two vertices are the two vertices that this edge connects, are they colored with two different colors or the same color? That's what we are doing when we are performing this edge checking gadgets. Basically, we're not able to solve NP problems due to hardware. No, so we are not able to solve NP problems because we don't know of any efficient algorithm for them. NP complete problems. Right, so it's not really a hardware limitation because you can pick the greatest and latest hardware and keep building them up. But because the algorithms run in exponential time, very quickly you'll run into limitations. All right, so what's happening here? It's a simple circuit that you can easily verify. We've been using CNOTs already. We use CNOT in the definition of oracles as well, or simple oracles as well, when we identified B sub F for promise problems. What's happening over here, the value X gets XORed into this additional qubit. So X gets XORed into this additional qubit by application of the CNOT, and then similarly, Y gets XORed into this qubit by application of the CNOT. So if this additional qubit is initialized to the state 0 by application of these two CNOTs, the resulting state will be X parity Y. And note now, if you imagine this X and Y as being this vertex, as being the qubits representing the vertices of a given graph, then this new qubit is essentially our edge check, where it will take the value 1 if these two qubits are colored differently, and it will take the value 0 if they're colored the same. And that's just a property of the XOR logic circuit, right? So whenever X and Y will be both same, this edge check qubit will take the value 0, and otherwise it will take the value 1. So that becomes a way of checking, is an edge connecting two different vertices, should it be counted or not? Because does it connect same colored vertices or different colored vertices. Now recall, we are looking at the special case of bipartite graphs. So for that case, all edges should be connecting different color vertices if the graph is indeed bipartite, right? If you identify the right bipartition, then each edge will be going across. Each edge will contribute to this edge check, right? So if I've got k number of edges, then I will have k number of qubits to identify an edge check for each edge in the graph. Right? So let's go through now an oracle construction for this particular graph, and hopefully this will kind of finally answer the question about, hey, where does the oracle come from? So obviously the first step, as always, apply Hadamard's, because I don't want to consider just one particular coloring of these four vertices, where these are the four vertices I'm considering. I want to consider the uniform superposition of all possible colorings. And then within each of those colorings in superposition, I would want to check, hey, is this a valid coloring or not, given that there are these three edges in this graph. Since there are three edges, I will need to do three edge checks. So I've got these 4 qubits for the 4 vertices, 3 qubits for the 3 edges, and 1 final qubit for the final answer, which we'll soon see how it works out. Any questions so far? If you understand this construction, then essentially we have the main construction of the algorithm done. All right. No one shouting out from Discord, so things should be fine, hopefully. All righty. So now we are just implementing this edge gadget that we saw previously, that, hey, there is an edge from 0 to 2. So, hey, this is the gadget that we identified, C0 from 0 to the edge check qubit corresponding to it, and from V2 to the same qubit. So this is the edge check for the edge 02. This is the edge check for 03. This is the edge check for 13. Now, if this graph is bipartite, which indeed it is, then all these three edges should contribute to the partition, to the cut, right? I.e., these two should be colored differently. These two should be colored same. These two should be colored same. This is one partition. This is one partition. My algorithm is saying, hey, let's consider all uniform superposition of all colorings. Within them will be this partitioning, this coloring as well. When you'll do the edge check for it, all these three qubits should evaluate to 1. So the reason why I've just colored them differently is to identify that these are the vertex qubits, these are the edge check qubits, and this is the answer qubit. Other than that, there is no difference. It's just one circuit, right? Just to distinguish the logical kind of reason that they're being used for, to distinguish between them. These are vertex qubits, these are the edge check qubits, and this is the answer qubit. All right. Okay. Now, so for the case of bipartite graphs, we just mentioned already, the insight was all the edges will contribute to the cut. So that means this qubit should be 1, this qubit should be 1, this qubit should be 1. I want to check that. So that means my answer qubit is initialized to 0. My first edge check, second edge check, third edge check, control on all three of them. If all three of them are 1, flip the answer qubit. So this will become 1. Now I apply the Z gate on it, and this introduces the minus sign in front of it. Hey, that's really nice. That means when I identify a valid cut, I've been able to identify this minus sign. That's really the crucial thing for the oracle in front of my qubits. Right, so quick recap. It's not that I'm considering one coloring. I'm considering the application of this Hadamard, all possible colorings. Within those all possible colorings, there will also be the colorings that are valid, indeed, if they exist. For those colorings, these three edge checks will make these three qubits 1. In that case, this multi-C0 gate will cause this answer qubit to get 1, to become 1. And just like in the oracle, the inversion around the mean operator, we saw application of the Z operator. Similarly over here, applying the Z operator to introduce that minus sign. And then all that remains is to undo the work of however we have changed these previous qubits, which means you think of all these transformations that we've done over here and implement the inverse of that transformation to make sure the qubits are back in the state that they were before this transformation was applied. Why are we doing that? Because the only thing that my entire oracle should do, which is now this entire big transformation, is put this minus sign in front of the cases for which f of x evaluates to 1. Nothing else should change. And so in order to guarantee nothing else changes, I just take all the transformations that I had applied other than the z gate, and I apply them again over here to implement the inverse transformations. Everything else is everything other than this auxiliary qubit is back to what it was previously. Yep, that's totally neat. So this entire thing hopefully then answers the question from yesterday that, hey, here's how do we implement the oracle? Well, here's the oracle that will implement the phase, oracle. Well, here's the circuit that will implement the oracle for our max-cut problem. Special case scenario, though, we have so far only considered bipartite graphs. But it's still cool and nice, because the logic really won't change much as we go from bipartite graphs to general graphs. Right? It's really nice. You should really work through examples of this for additional graphs as well to see what's happening. No, this Hadamard was this separate part, right? This Hadamard was bring everything in superposition. Number of edges as a value. Well, the number of edges are being checked by the fact that this qubit will only get flipped if all of these 3 qubits are 1. And so we know, since we are restricting our attention to the bipartite graph, that all the edges should be in the cut. And all the edges to be in the cut means that all of these need to be 1. Right? It's not an issue of this is 1 and this is not 1. And for sure, it's a special case scenario. And before we celebrate too much, here's the side note, right? So we have we've seen how to construct the oracle for bipartite graphs. Yes, after this oracle call, you can go ahead and do Grover's search and be done with your thingy. But the issue is, this quantum algorithm is O of square root of 2 to the n. Having said that, given our restriction to graphs for graphs to be bipartite, there actually is a very nice efficient polynomial algorithm that classically does the job for us. So yes, while it's great that we really did construct the oracle, because of the special restriction that we put on the nature of the graphs, we actually don't really get an interesting speed up for this particular case, because if a graph is bipartite, there's an efficient algorithm to figure out whether or not it's bipartite or not. Right? So, and kind of moving on to NISQ algorithms, whatnot, this is something to always keep in mind, right? So if you apply a generic quantum algorithm, such as Grover algorithm, to kind of some interesting problem, don't expect the speed up over there that's coming just from this, generic quantum speed up to always necessarily be able to overcome or be better than what's classically possible. So the classical algorithm for the case when the graphs are bipartite can really use this property in a much nicer way to identify a very efficient algorithm for identifying the bipartite structure of a graph. So you don't want to compare apples and oranges in the sense that, hey, here's a generic algorithm, whereas here's this fine-tuned algorithm for looking for bipartite structure. No, not capital N squared. It's small n squared. That's exactly the point, that it's polynomial. If it's capital N, then it's 2 to the n squared. That's still big. So for the case of bipartite graphs, right? That's the restriction over here. That in the analysis over here, we have made an assumption that the graph is bipartite. That's why in this step we were able to basically just argue that, hey, check that all of the edge check qubits evaluate to 1, because we know that for bipartite graphs, all the edges will have to be in the cut. Now, this obviously will change for a general graph. And here's how it will change. So the generic oracle construction, where we are removing the restriction of the graph to be bipartite, you still do the edge check. Then you need to now do some additional calculation, which we'll quickly see the circuit for, but we'll hold a separate programming tutorial next week that you can really work through the details of how this is working. But this is now, in some sense, all classical. There's nothing quantum now happening over here. So you say, all right, I will implement a summing operation on the edge check qubits. Over here in the circuit, I just said, hey, all of them have to be 1. But now if my graph is not bipartite, all of them don't need to be 1 for the right answer. And so I'll need to implement some kind of addition algorithm to figure out how many of the edge check qubits evaluated to 1. And then going back to this initial idea that in this optimization versus decision problem, I'll need to have this routine that will check, hey, have I identified a partition of size, cut of size k? So I'll need to have some kind of check. Again, this would be something kind of completely classical. There's nothing quantum about it, that I will need to check that the sum that I computed over here, is it greater than or equal to k? I'll need to store that value, and that's just going to apply the same. So the key 2 steps that are changing are these 2 steps for the general case that are different from the bipartite case. How is this check happening? As I mentioned, you would want to do the programming tutorial next week to really work the details of the circuit. But this is kind of a very similar, not identical, but a similar gadget as we did for edge checking. So imagine these 3 qubits, Q0, we had some graph in which there were 3 edge checking qubits, Q0, Q1, Q0, Q1, Q2. We've already done the edge checking such that their values have already been identified. And now I want to sum up these 3 qubits. So I'm not doing generic addition. I'm just saying, hey, take the value in Q0, which is either going to be 0 or 1, then add Q1 to it. Again, Q1 will always be either 0 or 1. So I'm at maximum, always just either adding a 0 or a 1. So I'm not doing generic addition of arbitrary 2 n-bit integers, which although can be done. Here, all that I need to do is say, hey, I need to store the addition of these 3 qubits. First, I take this qubit, I really don't need this over here, but for completeness, I put this over here. You can really get rid of this circuit, this specific C0 gate, and just apply the C0. Because in the beginning, the sum qubit will be 0. I just store the value of Q0 into Q3. Then I take Q1 and add it to Q3. And if there's a carry bit, this takes care of it. And then similarly, finally, I take Q2 and do the summation again. So essentially what I'm doing is that this becomes the sum qubit, this becomes the carry qubit, but the result of adding these 3 qubits. Naturally, this can be generalized to adding n qubits as well. But this example, I think, suffices to understand what's the general idea. Based on this, I will get some integer output that, okay, I've identified k qubits are 1, or k edges evaluated to 1. Well, the binary search structure is going to be something of exactly this form, number checking. Well, example, let's say if I've got 3 qubits, I'll check, that means 0 to 7 possibility, total 8 number of possibilities, 0 to 7. I identify right in the middle, is k greater than or equal to 4? I get the answer yes or no. If I get the no answer, I take the left subspace, divide it into half, do this search, yes answer, I divide up the right subspace, I look at the right subspace, divide it into half, and I do my binary search. Within this binary search, naturally, this k is actually not going to be represented in integers, it's going to be represented in binary. So I'll need a circuit representation, again, for doing this number checking, right? So this circuit over here was for the step 2. In the step 3, where I do this checking of summation, these are the kind of circuits I'll need to build. So remember over here, the check was for k is greater than or equal to 4. So for k is greater than or equal to 4, it suffices for me to check that the most significant bit is 1. If it's 1, doesn't matter what the other 2 bits are, the number being represented by these 3 qubits is greater than or equal to 4. And so that circuit will just be this C0. Right, so the answer over here will be 1 if the number being represented by these 3 qubits was greater than or equal to 4. Completely kind of classical reasoning, nothing quantum about it. You kind of go forth and do exactly this kind of reasoning with the binary search. So here, this is the circuit for is k greater than or equal to 2. That's the circuit for this. Recommend you verify that why is this the circuit for it. Similarly over here for 6. And so the idea is for each of these steps, I will need to run a Grover's algorithm, right? So I run a Grover's algorithm here. I run a Grover's algorithm here, so on and so forth. This is a binary search. So the depth of this tree will be logarithmic in the number of edges. So I will need to repeat this process. Now I'm talking about the arbitrary. I need to repeat this process logarithmic number of times in order to get to the answer. In each of those iterations, I'll need to have run my Grover's algorithm. All right, and so that gives me my generic algorithm for the number checking. For a subroutine, in the generic oracle call or oracle construction for max cut using Grover. All right. So lots to take in over here. Today's lecture was slightly condensed. I'm already over time, but I think the main parts of the algorithm have been conveyed. What still needs to be done, because I've presented to you lots of gadgets that we haven't really verified that they work correctly. Again, I want to emphasize all of these gadgets are something really completely classical. You can think of this as completely classical circuits with nothing quantum really happening here, and the same intuition and the same logic goes through. The key quantum part over here is really the Grover algorithm working on this uniform superposition input and the fact that this oracle construction does work out. So we note that, and again, connecting to one last question from yesterday, note in this case where we argue that for bipartite graphs, there is a classical algorithm that works of n square. This connects to this paper that was shared on Discord as well, right? So in the case where I can open up the oracle, I know the structure of the oracle, then the classical algorithm can do something better as well, right? So that's exactly kind of what's happening over here as well. That if I know that the graph is bipartite, the algorithm uses that structure to its advantage to get a more efficient algorithm classically. Whereas the quantum case, I'm really just applying kind of a generic tool of Grover's algorithm to get this quadratic search. Indeed, a quadratic improvement. In the general case, though, for sure, this result is not there, right? This best classical algorithm is only in the case when the graph is bipartite. As I mentioned in the beginning, if I don't have this assumption, then the classical algorithm is of 2 to the n, and Grover then is of square root of 2 to the n. So I do have a quadratic improvement over the general case of the classical algorithm. And with that, we end our discussion of Grover's algorithm. And I'll just end with this, my kind of favorite punchline for this, that quantum computing and all that we're doing over here is really allowing us this nice little kind of power of manipulating probability in a richer way than classical computing allows. And that's a very cool superpower to play with. Hopefully you had fun. Thank you.
Thank you, Jibran. This has really been a memorable week with a very steep learning curve from QBronze, QNickel. Great. Thank you so much. Really invaluable experience for everyone. And I see indeed on the chat by Raja, Oxy, Aniruddha. Thank you, Jibran. Thank you. Great learning experience.
Thank you.
Very happy with you being here and giving this amazing course this week. Great. Please keep it going. I think it's fully justified.
So there was a comment about whether I could consider this a hybrid algorithm. So a hybrid algorithm would be where, so Simon's algorithm, where I really do some classical post-processing that's really non-trivial. That's kind of a hybrid algorithm where you apply the quantum part of Simon and then you do this classical post-processing. Here, when I kept emphasizing the fact that, hey, this edge checking and et cetera, all classical, what I meant is that the logic of that is classical. I still kind of, these operations will be implemented on a nice giant quantum state in superposition, right? That's exactly why Grover at the end of the day will be able to give us the speed up, because it received an input state in uniform superposition. So the entire algorithm is indeed still completely quantum. It's just that the logic of these small gadgets that we were using for adding qubits or for checking whether the value is greater than or equal to 4 and stuff like that, the logic behind those was completely classical. We weren't really doing anything quantum to do those computations. So.
Wonderful. Giuliana from Italy says, the last part on complexity was great. Artem says, amazing lectures. We cannot thank you more, Jibran. Thank you so much.
It's wonderful. Thank you.
In the meantime, I will share about next week what we're going to do. And for Dan, if you're there, please join me to share more about the prerequisites for the software bootcamps. First of all, more mentoring sessions coming up. On Sunday, 9 a.m., 10 a.m. ET, tutorial with Cirque, tutorial with Qiskit, and on Monday, quantum mechanics concepts for quantum computing, all led by both QWorld and CQ Tech. Then a really exciting week is starting. While this week focused more on keynotes and QKD and quantum algorithms, next week we will start with the hardware. We will have David DiVincenzo give a keynote on quantum computing. We will have the hardware lecture on neutral atom quantum computing right away on Monday. And then take a deep dive into superconducting quantum computing with a lecture, superconducting quantum computing with a virtual lab tour, and on. This will be alternated with software boot camps. On Tuesday, after you learned more about the hardware of neutral atoms, we will do a software boot camp on neutral atoms together with Pedro Lopez from Quera. And then on Thursday, how to solve the traveling salesman problem with QUBO formulation by Terra Quantum and QMware. Vardan, would you like to share more about these boot camps and the prerequisites?
Absolutely. So hello, everyone. As Malu had just mentioned, next week we are diving deep into the specifics of quantum algorithms. There would be super exciting boot camps to follow up and really, really amazing hardware lab tours. And these lab tours have been like really awesome last year as well. Our participants were really happy with that, and we are sure that you will find that really, really exciting. But apart from the hardware lab tours, I wanted to speak a bit about the software boot camps. These boot camps are designed in a way that they would guide you right from the start to the end of a very specific problem, which is kind of an application in the industry today. So these are typically an hour to 3 hour long sessions, and they would cover everything. All the software boot camps are independent of each other. So it's not like what you had this week, where each session was a continuation of the last one. These software boot camps are all individual sessions. Talking about the prereqs, I would request all the participants to try and complete QBronze and QNickel over this weekend. You would have Saturdays and Sundays to you. There are, I think, a couple of office hours as well, which are generally hosted by QWorld and the Secretary team. These are awesome. You should go at these office hours, attend these sessions, and get all your doubts, queries solved so that you know how these quantum algorithms work. Just the knowledge of QBronze and QNickel should be enough for you to actually participate and learn something new during the software boot camps. Another small point about the prerequisites about Python. Python will be really important for the next week. So all the participants who are from a computer science background, I believe you already know all the stuff about Python and programming on that. But those who are coming from different background, Python might be something new to you. So I would advise over the weekend, try installing all the libraries, try getting all the Python stuff done on your local computers. Try installing the Conda environment, get familiar with it, try Qiskit locally on your computers as well. So that next week during the software bootcamps, you can actually learn and do hands-on training during the program itself. There will be some additional prerequisites as well, according to specific bootcamps. So each bootcamp would have something which you might have to install on your computers, or some documentation which you might have to go through before the program. And those would be announced on Discord, so keep an eye out for that as well. Those would be announced beforehand in advance, might be over the weekend or definitely before the session. So once we announce that, each and every participant is requested to download and get ready with all the stuff before the bootcamps, because in the bootcamps we would actually be doing hands-on stuff. So yeah, and yeah, get ready for the next week.